Hi, today we're going to talk about rotational inertia. And rotational inertia, you can think of the mass as inertia, and then rotational inertia is the rotational analog to mass. In other words, rotational inertia, well, if you think of inertia, it's how hard it is to speed up or slow down an object, really to change its velocity. Rotational inertia, how hard it is to speed up or slow down its rotation. Okay, and the way we use that, sum of the forces equals m, the linear inertia or the regular inertia, times the acceleration. And we use rotational inertia with the sum of the torques equals the rotational inertia times the angular acceleration. Really pretty much the same equation, just with rotational variables down here. Excuse me. We also use this rotational inertia for momentum, just like we use P equals mv linearly. Rotationally, we use L equals I times omega. We also do the same thing with rotational kinetic energy. Kinetic energy is 1/2 mv squared in a line, but when we rotate, it's 1/2 I omega squared. So the equations are very familiar, but we need to use these different variables. And the reason that rotational inertia is not the same as mass is you can think of it's harder to twist something when I use a pencil, and if I rotate it like this around the center of mass, it's easier to do than if I rotate it like this around the end. There's more rotational inertia. It's hard to change its angular acceleration. So let's talk about this. Let's talk about how we actually calculate rotational inertia. Just like in that pencil, with rotational inertia is greater if the mass is farther away from the point of rotation. So if we use r to be distance to point of rotation, then boy, I'm having problems there. Rotation, then I is going to be the mass times r squared. Okay, so more mass, more rotational inertia. Farther away the mass is from the point of rotation, more rotational inertia. I'm going to fly right through this because what I want to get to is how we find rotational inertia for different situations. You can look up tables and you'll find rotational inertia for the center of mass for a bunch of different objects. Okay, for a rod around center of mass, I equals m times the mass of the object times the length of the object squared divided by 12. For a disk, flat disk, I center of mass equals m times the radius of the disk squared divided by 2. For a sphere, it equals 2/5 times pi, times m times r squared. 2/5 mr squared. I'm going to show you how we get these in the next video. For the current video, I just want to talk about, if we're given these, how we find the rotational inertia for compound systems. And the thing that allows us to use these sorts of rotational inertia statements, and this basic one for a point source, mr squared, is this thing called the parallel axis theorem. Parallel axis theorem. And the parallel axis theorem, very, very important, tells you that if you know the rotational inertia around the center of mass of an object, then if we move that rotational point away from the center of mass, this new rotational inertia of that object is going to be rotational inertia for the center of mass plus the total mass of that object times x squared, where x equals displacement from center of mass. In other words, where our axis is, how far our axis is away from the center of mass. Only true if the axis we rotate it through is parallel to the axis we started. So for example, let's take a disk right here. If we rotate it through the center of mass, we know the rotational inertia is mr squared over 2. If, on the other hand, we consider it rotating around here, I'll put a little point here, P, the rotational inertia would be, let's look at this, the new rotational inertia will be the rotational inertia around the center of mass plus m times how far we've moved this axis. Okay, so we look it up and we say I prime equals I center of mass, which is mr squared over 2. And remember, this axis would be straight down through the disk. And this new axis is going to be straight down through point P. So in other words, the disk would be rotating this way, or the disk would be moving around point P in this direction. But these two axes are parallel, so we can use the parallel axis theorem. So there's I center of mass, and then we want to add on this term, mass times x squared, how far we're moving that center of mass, mx squared. Okay? So we're almost done. Now, all we want to do for complex systems is apply this parallel axis theorem if it's off center. If it's not on the center of mass, we apply the parallel axis theorem over and over for each object in the system. So let's just say I've got a rod here. I'm going to try to make this fairly thin because that equation is for a thin rod. Okay. And I'm going to say here's my point of rotation P. Okay. At the end of this, I'm going to put a disk, right there. This has a length L, a mass mr, mass of the rod. This has a radius r disk and a mass m disk. And then let's just put a point somewhere. The mass m point, and it's at a distance. Boy, we're getting a little busy here. There we go. R point. Okay, so there's a bunch of things going on here. You've got a uniform disk. You've got a uniform disk, a uniform rod. Inertia is total rotational inertia is going to be, I'll put total, is going to be the rotational inertia of the rod plus the rotational inertia of the point plus the rotational inertia of the disk around, and we use this expression, around point P. In other words, we're considering point P to be our axis. So let's take a look at that. Let's see how that works out. I have to move my camera because I'm getting a little off the chart there. Okay, there we go. So let's start with this one. The rotational inertia of the rod about point P is going to be I center of mass of the rod plus mass of the rod, we're going to use the parallel axis theorem, times x squared. Okay, x, the center of mass, is right here. So the distance we move that center of mass is L over 2 squared. In other words, from the center of mass of the rod to point P is L over 2. Okay? And if we break that down even further, we have I center of mass of a rod is ml squared over 10, mass of the rod times the length of the rod squared over 12, plus mass of the rod times L squared over 4. Okay, all I've done is rewrite those. Now let's get that point mass. That's an easy one. For a point mass, it's just mass of the point plus this distance squared. Plus times that distance squared. Sorry about that. Let's carry that down. MPRP squared. And then finally, for the disk, we add the mass, the rotational inertia around the center of mass, let me write that right, M disk times R disk squared, that's RD squared over 2. And then we've got to use the parallel axis theorem, the mass of the disk, times the distance from the center of mass to our point of rotation, that happens to be L, quantity squared. So I wish I'd written that as I center of mass disk, but I hope you get the idea. Okay? And I'm not going to go through the math adding those together. You can combine some terms here, and you should be able to come up with an expression for the total rotational inertia about point P. Next time what we'll do is we're going to talk about rotational inertia. We're going to integrate to figure out how we get some of these different equations for the center of mass.